the first one there. You can highlight that heading on page 40 below the chloroplast, factors affecting the rate of photosynthesis. Highlight carbon dioxide. Now, as this graph shows, that on this axis we have the amount of CO2 increasing in that direction, isn't it? If we had to put 0 there and put some values, we are looking at things like 1, 2, 3, 4, etc. And then the rate of photosynthesis obviously increasing, going upwards on your y-axis. So if I had to put a point there, that shows me that that is the point where the rate of photosynthesis is the highest, or is at its optimum. Then that means that this amount of CO2, what are they measuring it in? Well, maybe parts per million, right? 3.5, isn't it? Would be the optimum amount of CO2 that this plant requires to photosynthesize at its highest rate. So the pattern of this graph tells me that as the amount of CO2 increases, so does the rate of photosynthesis until an optimum is reached. After that, what happens is that there's excess CO2, too much of CO2. Look at this beyond this point. Isn't there more CO2, more CO2, more CO2? So beyond that point, the excess CO2 actually combines with the water, because remember that the plant is using a certain amount of CO2 for it to photosynthesize, as well as it's using water. And what happens when the CO2 becomes more than is required? It becomes in excess. So that excess amount is going to combine with water and it's going to form something called carbonic acid, right? That's H2CO3, which you've got it there in the word form, carbonic acid. You can see the H from the water and your CO from the carbon dioxide. So that is carbonic acid. Because it's an acid, we know that means low pH. pH affects enzyme function, isn't it? So if the pH is too low, in this case, it can damage your enzymes. It would denature it. What enzymes are we talking about? The enzymes involved in photosynthesis. We spoke about light phase and dark phase, and that enzymes are present there that are produced by the ribosomes in your stroma, and they are there to catalyze the reaction of photosynthesis. So when these enzymes denature, they are not going to obviously perform that function of catalyzing the reaction. What happens? You see that photosynthesis therefore decreases. The other way that this graph can be depicted, and let me just, is like this. In this case, that's the optimum right there. Okay, no, there, see, that's higher, isn't it? At that point, the rate of photosynthesis levels off, meaning that there's no increase, right? There's no, in fact, it's mainly depicted like this in this graph, as opposed to this, which is in your study guide. So this is showing that it starts to drop, right? Here, it starts to level off, meaning there's no more further increase in the rate of photosynthesis. But you just need to have a basic understanding of how CO2 affects the rate of photosynthesis and how to identify the graph of it and where it's the optimum. What happens when CO2 starts to increase above excess? Speak about becoming carbonic acid, lowering the pH, enzymes denature, and then photosynthesis rate decreases or cannot increase any further. Next one, let's look at I've got temperature, you've got light intensity, temperature. Okay, let's do temperature. Temperature, as the amount of temperature increases, here increasing, if we can put some values, I'd put this as 25 degrees Celsius, and somewhere along there is 10, etc. Okay, that means that at 25 degrees Celsius, that is the optimum temperature for this plant to photosynthesize, and that is speaking about mesophyll plants or mesophytic plants, where they are able to photosynthesize at normal room temperature, right? So 25 degrees is generally the optimum temperature. You've got the word there on your book, optimum, best. Okay, as temperature increases, so does the rate of photosynthesis until the optimum temperature is reached. After that, the temperature becomes too high, or causing the enzymes, yes, you know it, to denature. Denature, change shape, and then therefore they cannot catalyze the reaction, as we discussed above there with the CO2, and therefore the rate of photosynthesis will start to drop or decline, right? Enzymes have become denatured. But what about, let's say you get asked a question about low temperatures. Why is the rate of photosynthesis here low? And temperature, we know, is low temperature. Then you're going to speak about the fact that enzymes at low temperature, they are inactive, right? So therefore the reaction is going to be slower. When they have an increase in temperature, that's an increase in energy as well, for the enzymes to actually start moving around and lock onto their substrate, you know, enzyme lock and key model. And you learned about high temperature, low temperature, where low temperature makes it inactive, and high temperature, too high, would denature it, right? So at low temperature, we're going to speak about the fact that your enzymes are inactive. You're going to highlight that on page 41 at the top there, and write the word mesophyll, where you see 25 degrees as being the optimum for your mesophytic plants, right? Then go back to page 40 at the bottom, where we can look at light intensity, right? Here, right? So light intensity, there's no measurement there, but generally kilolux, as the amount, or as the intensity of light increases, so does the rate of photosynthesis, right? We expose a plant to more intense light, it's going to be able to photosynthesize at a higher rate, and that is because, yes, we know the plant requires light energy, right? That is going to be absorbed by chlorophyll and chloroplast, etc., and the reaction of photosynthesis will take place. But you can see that this graph has double lines, right? It's a double line graph. It's representing not only light, but it's representing light intensity at different temperatures. So it's a graph that's showing you two factors, two external factors. In fact, that double line graph can be also applicable to temperature and to CO2, where I can have another limiting factor that will also limit the rate of photosynthesis, but depicted by a double line graph. So we're seeing it here with light intensity. We are seeing that there are two lines, but one reaches an optimum at an earlier point as compared to the other. See, at 20 degrees Celsius at a high light intensity, right? The optimum was actually reached at a lower light intensity, right? But what is the rate of photosynthesis? Somewhere around there. But at a higher temperature, at 25 degrees, which is the optimum temperature for mesophytic plants, and at an increase of light intensity, the optimum, or the highest point that it reached, is somewhere there. Now, isn't that higher than this one here? That shows us that at an optimum temperature for photosynthesis, the rate of photosynthesis increases as light intensity increases. However, if temperature is not optimal, then the photosynthesis levels will be much lower at lower light intensity. Hence, temperature can be seen as a limiting factor, right? We can see here that it starts to level off from an earlier point as compared to there, and that this is optimum, is a higher optimum than this one, because we've got temperature that is playing a role here. So temperature becomes a limiting factor here, right? Because I'm using it with light intensity. But generally, as light intensity increases, so does the rate of photosynthesis, okay? But at any increase in light intensity beyond the optimum point, or beyond the optimum light intensity does not give us an increase in the rate of photosynthesis. What happens is it levels off and there's no further increase. So we're seeing optimum being reached and then we're seeing it leveling off.